Conventional fire alarm systems. In this presentation, we're going to be looking at conventional Class B, conventional Class A, and dual stage conventional fire alarm system operation. Conventional means no communication is present between the devices and the fire alarm panel. Instead, the fire alarm panel determines what is occurring in the devices and the wiring by evaluating the level of current measured. Conventional devices are very simple in construction and operation. Sometimes conventional fire alarm systems are referred to as non-addressable. Here's an example of a conventional fire alarm panel. They're usually fairly small, with a limited number of interactive push buttons on the front for navigation within menus or anything, and often many of them are not even programmable. At the bottom would have been where the battery pack is located. This one they happen to be removed. Fire alarm devices for conventional systems can be divided into two categories. The first one is the notification appliance circuit, abbreviated as NAC or NAC. These are the devices that notify the occupants of a fire. The second category is the indicating device circuit, abbreviated as IDC. These are devices that sense smoke or heat or are manually operated. These abbreviations will be used in the field to describe the wiring of these two different types of devices. If we take a look at a horn strobe, which is a NAC device, we'll see that there is a third device or third object in addition to the horn and strobe. It's a diode. Whereas on a standard pull station or even a heat or a smoke detector, often it's a very basic operation of simply a contact closing. First, we're going to take a look at the operation of an IDC circuit, which is the detecting devices, and then we'll come back to the notification or horn strobe. A Class B conventional system that we're going to look at requires the use of an end-of-line resistor. The end-of-line resistor is used to restrict supervisory current. Its size is determined by a fire alarm panel manufacturer and is typically terminated on the back of an end-of-line cover plate at the end of a fire alarm loop. Well, let's see how all of that gets terminated. Here's an example of the connections for the IDC loop of a single pull station, and you'll notice at the far end an end-of-line resistor. Now it's important to understand that for an IDC loop at the fire alarm panel, the source polarity is constant and never changes. This connection is current limiting, meaning it will restrict current in the loop when an initiated device is activated. And we can see here the initiating device is actually in parallel with the source, so positive and negative side of the source, which will cause an increase in current. But what about that end-of-line resistor? Well, the presence of supervisory current, which is what I'm showing on the diagram right now, proves that the conductors are intact and that the pull station is connected in the circuit. The value of supervisory current is of course determined by the size of the end-of-line resistor, and the fire alarm panel is continually monitoring this current. If for some reason the current would drop to zero, it would signal to the fire alarm panel that there is a problem in the wiring or perhaps a removal of a device. In either of these situations, the fire alarm panel should go into a trouble condition. And we can see the removal of a wire from a pull station would elicit the same response as the supervisory current would drop to zero. Now if we take a look at a normal operation or normal condition fire alarm panel, in the event of a fire, a detecting device will be triggered. In this situation, a pull station. Now this will elicit an increase in the current. Right now we only have supervisory current, but when the pull station is pulled, that will cause an increase in the current, and that's because we've got a parallel branch here. Now of course, the connection is current limiting, so we're not going to have a short circuit and a fire, which would be ironic at best. So this will limit the current in the loop when the initiating device is activated. And the fire alarm panel will then recognize this amount of current as triggering of a detecting device and send the panel into an alarm condition. That then brings us to the notification circuit and the horn strobe. Why do we have a diode in there? When we have a diode in a circuit with a DC source, it acts as a one-way polarity sensitive switch. In this particular orientation, the diode is blocking due to the DC source polarity. That means it's reverse biased, and it means that the horn strobe remains off. If we were to take the wires and reverse them and connect them, The diode would then be conducting due to this DC source polarity having been reversed, and it would be forward biased, and the horn strobe would be permitted to then energize, and all of the flashing lights and the horns would sound. A fire alarm panel is designed to reverse the polarity of the NAC loop terminals to turn on the notification appliances during an alarm condition. And there's a reason why we do it this way instead of just turning them on and turning them off. So here's an example of a notification appliance connected in, and the fire alarm panel normal condition, it's blocking. When it senses from the IDC side that there is a fire, right, it will then go into alarm and it will reverse the polarity of those two terminals to the NAC circuit. And that will cause the NAC devices to energize. What's interesting is that if an individual were to connect the notification loop to the fire alarm panel with reverse polarity to begin with, the very first time it's turned on, all of the notification appliances would then sound, and it would be rather funny. Now, the real system, as in the notification appliance circuit, will always have an end-of-line resistor for Class B. Class B simply means that we have an end-of-line resistor in the circuit. So in this situation, now we can see why the system is designed to flip the polarity, because we need to constantly have a source connected to the wires so that we have supervisory current. And the supervisory current proves the existence of the wires, that they're intact, and that everything is A-OK. We haven't removed a horn strobe. In the same way, on the notification circuit, if there was a break in the wire, the fire alarm panel would notice the drop in current down to 0 and would send the fire alarm panel into a trouble condition. Of course, removal of a wire from a notification appliance would elicit exactly the same situation. Now, what will happen when the fire alarm panel goes into alarm? Well, when it goes into alarm, it will change or flip the polarity of the two terminals for the NAC circuit, and that will then allow for the diode to go into forward bias and allow current to flow through the notification appliance, therefore alerting everyone to egress or evacuate the building. If we take a look at the terminations on a standard conventional panel, you'll notice that they're all laid out in pairs and labeled. So we can see at the top NAC1, NAC2, and down near the bottom IDC1, IDC2, IDC3, and each of them has an indication of polarity, negative and positive. Notice the black rectangular boxes to the left of the NAC terminals on the top of the photo. These are microswitches which are used to reverse the DC polarity of the NAC enunciating devices. Unused NAC or IDC terminals require the end-of-line resistor to simply be terminated across them so that the system knows that there's something there. Otherwise, you won't actually get the fire alarm system to function. Now, wiring of conventional fire alarm devices is important. IDC and NAC devices both require terminations which make the removal from the fire alarm loop obvious to the fire alarm panel by the drop in supervisory current. And that means that we always want to have independent terminations of every wire. So on this gong, which is a NAC device, there are 2 reds and 2 blacks. We don't just take one moret and tie all 4 wires together, although that's what you would do with a receptacle. Instead, we keep each one independent, so that if someone were to remove the bell, they would have to interrupt the current, supervisory current that is, of the line conductors here, and that would trigger the fire alarm panel into trouble. In the same way, when we have terminals on the back of a device, you're not going to twist them both together and then insert them underneath one side of the screw, but they must be left independent. Again, the reason for this, doing the moret thing, is because we want to make it obvious the removal of the device. Right now, the device will certainly work if we go into alarm. I mean, the device is connected across the terminals of the NAC, and right now we are sensing supervisory current. The problem comes in if someone were to remove the device entirely. The fire alarm panel has not noticed any change in supervisory current, and that's because there has been no interruption of the circuit. And so this becomes a very dangerous situation. This then would be a standard conventional fire alarm system Class B. We have a separate loop for the notifying and a separate loop for the detecting. Notifying is known as NAC, detecting is known as IDC for a conventional fire alarm system. When a pull station is pulled, the current value will rise in the IDC loop, at which point the fire alarm panel will recognize this current as an alarm condition. It will then change the polarity of the NAC terminals, and the devices will then energize on the NAC loop. Often, a conventional system will have multiple NAC and multiple IDC, and each one of these is then taken to a different location within a building. When multiple device loops are connected back to a fire alarm panel, they're often referred to as zones, and each zone requires its own end-of-line resistor. The diagram shown on the right is of the different fire zones of a large building. Various fire alarm standards will determine where the boundaries are for each of these zones. For a conventional system, each zone would have a separate IDC loop run to it for the initiating devices. NAC devices would then be placed throughout the building at strategic locations to ensure equal coverage of light sound in all the areas. Where NAC device loops are required will again be determined by fire alarm standards. Now, Class B conventional fire alarm systems have a problem. If a wire is broken or a device removed, all devices downstream will then become inoperable. So if we take a look at our standard situation here, if I have a break on the notifying loop right up by the end-of-line resistor, certainly the fire alarm panel will go into trouble. However, all of the devices will still be capable of operating during an alarm. If, however, we change where the break is to this location, the system will still recognize a trouble, but the last notification device on that loop will no longer be operable during an alarm. It doesn't have a connection to the source. Worst case scenario would be right up here, the first device on the zone. Man, if that were to happen and we went into an alarm condition, none of the notification appliances would function. Likewise, the same thing would occur down on the IDC. If we had a wire break at the very beginning before the first device, none of the indicating devices or sensing devices would be able to cause a change in current in the conductors and tell the fire alarm panel that there is a fire in the building. Therefore, the fire alarm panel would never go into alarm. If a wire breaks or a device is removed in a conventional system, the fire alarm panel will only indicate which zone the trouble is in. The electrician will then have to walk and inspect the entire loop in order to find the problem. In order to unpack a Class A system, we're going to start with a Class B, and you'll notice that all we're going to do now is we are going to remove the end-of-line resistor for both, and we're going to run the conductors all the way back to the fire alarm panel. Now, most panels are designed to account for one or the other. It's up to you and up to the engineer and up to the fire code standards which of the two you choose, Class A or Class B. Now, the advantage of having a Class A is that now we have return conductors going back to the fire alarm panel. There will still be supervisory current, and the supervisory current will flow through these conductors. It's as if the end-of-line resistor is located back at the controls of the fire alarm panel board itself. In these situations, the advantage of using a Class A is that a break in the wire no longer renders all of the devices downstream inoperable. There is no downstream because these devices here on this IDC loop could have been supplied from these terminals or from these terminals. And so in this situation, with a Class A, all devices remain capable of operation. Even if there's a wire break on this conductor, fire alarm panel connection is still provided from the original two conductors and all devices remain capable of operation. It really doesn't matter where the break is or even if both the conductors are severed. And so a Class A is considered to be a higher threshold of safety. Now, Class A conventional fire alarm systems operate exactly the same as Class B. They're simply safer when considering the implications of broken zone conductors. Now, often, conventional fire alarm system IDC and NAC loops are designed and wired in different classifications. And what I mean is that given 4 different fire alarm systems, the NAC and the IDC might be the same class as in both B, or they might be both A, or they might be different. This top one is the most common situation that you will find in industry. The IDC is Class A, and that's a higher threshold of safety, but the NAC will only be Class B, and that's because usually NAC circuits are wired with thicker wires, and that's because they're loads. And to have a return set of conductors from a NAC device all the way back to the supply can often be a fairly costly endeavor. And so, trying to balance cost and requirements for life safety, the top one is the most common application. If we take a look at some of the other terminations on this conventional fire alarm panel, there will often be dry sets of contacts that are provided. A dry set of contacts is simply a set of normally open and normally closed contacts, exactly the same as what would be seen on a standard relay. There is no voltage brought to them, rather their operation is controlled by the fire alarm panel, as in the normally open close when the fire alarm panel tells them to close. And so you can see them all listed and labeled all the way down here. We have trouble, we have supervisory, and we have alarm. So most control panels or fire alarm panels will provide a set of normally open and normally closed contacts for each of the conditions alarm, trouble, and supervisory. When the condition occurs at the panel, the contacts which are provided on the left-hand side will then change state. And so we can use those to control things like fire dampers and fire doors. Stage refers to how many steps are necessary for the fire alarm panel to go into alarm. On a single stage system, pulling initiates an alarm signal to the fire alarm panel, and that's because the current increases and the fire alarm panel recognizes this, and off we go. Most common fire alarm systems for buildings with able-bodied individuals will use a single stage. False alarms are an inconvenience, but not a large logistical problem. Dual stage systems are a little bit different. Pulling initiates an alert to the fire alarm panel. The key is then used to operate that particular or any fire alarm pull station and initiate a full alarm. So pulling the station initiates an alert. This warns building occupants that there may be an emergency. Prepare, but there's no need to evacuate yet. This alert might be with a sporadic or temporal tone of the NAC devices, or it could be a pre-recorded message over speakers indicating to people that there is the possibility of evacuation. Healthcare facilities, hospitals, nursing homes are all areas that an unneeded evacuation could require considerable labor and inconvenience, even risk, to the occupants. The intent of the keyed operation is to limit false alarms by requiring confirmation from an employee or security personnel sent out to investigate. If a fire is confirmed, the key is inserted into a pull station and turned. And you can see on this dual stage pull station, there are two sets of contacts. The first one is a switch, like the toggle switch when you pull down the handle. The other one is initiated by the key, and we can see the keyhole shown there or pointed to by the blue arrow. After a predetermined amount of time, the fire alarm panel will initiate an alarm regardless if a key is inserted or not. So this is what the wiring would then look like. We've got two dual stage fire alarm pull stations, and the two stage means that we have two separate lines of wiring, which need their own independent end-of-line resistor. The two don't mix together, they're completely independent through the whole path. What we'll typically notice is that only the key actuated switch inside the pull station is connected to the alarm IDC loop. All additional detecting devices are simply connected into the alert IDC loop. And remember, the purpose in doing this is to avoid false alarms and people all evacuating when it was unnecessary. So let's see how all of this then works in a large system. This is a conventional fire alarm Class B dual stage. Now we could have this as Class A as well, but just for clarity, I am sketching this out and describing it in a Class B system. So let's say someone comes along and pulls the pull station. What it will do is cause an increase in current, but only on the alert wires. And the fire alarm panel will have been set up in such a way that it identifies that increasing currents on the IDC alert loop and it goes into alert. So now we have a pre-recorded message on speaker saying there might be a fire emergency. We're looking into it. Please stand by. Now there's a certain amount of time that it takes for either a security guard or this facilities management to go around and just sort of confirm, is there a fire or not? So here comes the security guard, and they have confirmed that there is a smoke or fire visually. And so what they do is they come along with their key, they insert it into any pull station, and they twist it. And what that does is it closes the second set of contacts within the pull station, which causes an increase in current on the alarm IDC loop wiring. That then causes the fire alarm panel to acknowledge that there is a full alarm now, and it will trigger the notification appliances to turn on by flipping the polarity of their terminations.